So previously we've seen these in three integrals above. We recognize the first one as a scalar line integral. And then the second one we recognize as a vector line integral. And then the last one we just saw is, and this big S is meant to denote a surface, so this is meant to be a scalar surface integral. So then, well, let's see, so we have the scalar line integral matching the scalar surface integral, vector line integral matching maybe a vector surface integral. And that's exactly what this next definition is about. So we have a parameterization of a smooth surface, and we have this surface in a continuous vector field, and we're saying that the domain, or the parameterization, the domain of that is a subset of this continuous vector field, just meaning that it lies in the vector field. And so the vector surface integral is actually kind of what you might expect. So in it's f dot ds, where s is our surface, but more specifically, it behaves according to what we might expect from our vector line integral. So we would have to substitute the parameterization into the vector field and dot it with ts cross tt, which was our unit normal vector. So that's really nice. Another name for the vector surface integral that we're going to use instead of saying vector surface integral all the time is just flux. And so now this term of flux, we've seen this before, and I'm just going to show you what we did back in 3.4b, so I have it handy here. If you need to access your notes, please do. But in 3.4b, we were talking about the divergence theorem in the plane, right? And so here, we were saying, okay, our context, we were talking about D is a region in which Green theorem applies. Oh, we might need to remember those assumptions. But then we were saying that, okay, N is outward pointing unit normal vector to D, da da da, and then really, okay, so we had this closed integral over the boundary, and then we were saying that this is, that, and we were defining this closed integral of f dot n as the flux of f across the boundary. So, and really where that came into play was saying that we were looking at the total flow across the boundary and comparing that to net flow over the region, and we eventually said that those were the same. So flow is just really discussing, how much is going, how much is coming across the boundary. Okay, and so we're going to use that idea here in our understanding of vector surface integrals. Okay. So geometrically, how should we think of flux? Well, it's just a measure. Let's get this down. So it's going to be a measure, or it measures, rather. It measures the flow of the vector field, and I'm going to abbreviate vector field, of x across the surface S. Okay, so just adding up how much is going across our surface. Okay, and to that end, we have an example here. So S is a surface in the xz plane defined by that, so really just a square, and we have a vector field that is operating only in the y dimension, and so we just want to compute this, which is to say find the flux. So again, we would start this per normal. So according to the definition, I would need to get a parameterization going for the surface, and that happens to be x of s and t, right? And we know that the surface, since it's only in x and z, well, I can parameterize that quite easily as s, comma 0, comma t, and just say that s and t both live in 0, 1. Okay, so then when I do the parameterization, which happens to be really nice, when I compute the unit tangent, or when I compute the tangent vectors, I get 1, 0, 0, and I get 0, 0, 1, and then when I cross them and take their length, or sorry, I just need to cross them, I don't need their length for the vector surface integral. So when I cross them, TS cross TT, okay, you can double check me on this, but we should get 0, minus 1, 0. Okay, and then now in computing the vector surface integral or finding the flux, I would have a double integral of both from 0 to 1 of f of x of s of t. I'm going to add vector symbols in a moment over those, and then dot that with ts cross tt, and then ds dt, okay, which is going to be precisely 0 to 1, 0 to 1, and f of x of t. So when I substitute this in, I believe I should get 0, 1, 0. Okay, mainly because f, I mean, there's nothing to stick in, but there we go. And then I dot that with 0, minus 1, 0, ds dt, and I just get 0 to 1, 0 to 1 of negative 1 ds dt, and as you might imagine, we just end up with minus 1. Okay, so that is to say that the amount of flow over the vector field is just minus 1. Right? So we'll continue to discuss flux for almost the rest of the videos in some way, shape, or form.